Start the recording. I don't want to forget the recording. And I need to open up, James.
Hello.
What do I need to open up?
What do you need to open up?
Epic pen.
Epic
Pen.
Pen.
Hey, before I even go into this stuff, I wanted to show you something that Mike Zaransky just did. And, whoops, come on, go away, go away. This is the coolest thing ever. It is this thing called local storm reports.
Okay.
So Mike has recreated this. Let me throw you guys over here. He's recreated this page. So you know how we have a warnings page that looks like this? Have you seen that one?
Yeah.
This one is a local storm report. So you know how we always have to go through the weather service to go get local storm reports?
Mm-hmm.
Now we have local storm reports in time. So we can actually monitor this page and watch what reports are coming in. So here I've got non-thunderstorm wind gusts, snow, flood, heavy rain. These are all LSRs, tropical storm. I saw one that I didn't even know existed.
So the page will auto update?
It updates every 2 minutes. Storm surge, tropical storm. There is one, let me look for it, and then you can search it. So if I need to find debris flow. So there's a debris flow warning coming out of Puerto Rico, I guess, and Virginia.
Yeah, I've not seen that one before.
I didn't even know they had that. But let's say that I wanted to go, what happened in Illinois the other day? I go to Illinois, and we have it ordered. We can arrange it by state. So we can see thunderstorm wind gusts, 61, 66, 64. That's all Cook County. So if I said, well, let's go what's going on in DuPage County. Let's see what they had. As soon as you type in the little search bar, it'll tell you, okay, we had 4 severe thunderstorm reports. Woodridge, York Center, Carroll Stream, DuPage Airport. Come on, don't tell me that's not cool.
It's cool.
It is nice. Very
Winnebago County.
That's actually really cool.
I'm telling you, this is what we've wanted for so long, and Mike finally was able to do this. So we have some amazing stuff with this. So if I wanted to see tornado reports, rather than going to SPC to see the tornado reports where you see the dots, and we can create an image with these things in there as well eventually. But if I wanted to see tornado reports that have come in recently, then I've got Davenport office had a bunch. It looks like it's all the same tornado, but they did have a tornado. This would have been in Mercer and Rock Island County. So there it is. But if you say, oh, you know what, I want to measure snowfall. Okay, and let's say that we're doing it for Illinois. I can do it by state, and then I'll just do it. Okay, here's Idaho. So then you're looking at this, and you will always see snowfall reports coming in by state, Idaho. And we would do the same thing for Illinois. So if you want to monitor reports, rather than going to our text page, we have to search every single stupid text product and then go, what's that say? And then, oh, that's not the one. That has driven me crazy for years. And now it's all gone. So if you want to write down this, I can share it with you.
Are these the same reports that go down to SPC or show up on the SPC's page?
Yeah. These are, so let me show you. I'll give you this. And if instead of LSR, you do SVR, then you get the same stuff that we have with just severe thunderstorm and tornado warnings. And I think we have one where we include floods and any warnings that are currently going on. So we have a lot of these pages that are great ways to monitor. We just are waiting to get it done. It's taking a long time to fix things. So let's see, what else did I want to show you? Oh yeah, on the text page, See, the way you did it before, Jim, is you'd go to the National Weather Service forecast pages,
Mm-hmm.
and you'd go to miscellaneous, or no, I'm sorry, information, and you go, okay, local storm report. Okay, so sometimes they'll come up with this page where they summarize it,
Mm-hmm.
but it's just fairly random. And most of the times, like at the bottom of this, no, hold on, this is not working quite right. If I went to local storm reports, then at the bottom of the page, you'd see, go to previous bulletins. And they would come out there, one report, and you're like, okay, that's not it. And you'd have to search each text product to try to find where it is.
Yeah, I have access to NWS chat, so I see the raw data come in that eventually gets turned into this.
Right, and then they turn it into these reports, but that takes forever. So each one page is bad. So that's why this is going to be great. Anyway, let us go. I'm going to share the screen. Oh, I am sharing the screen. I'm going to start the movie, and we have our epic pen.
Epic pen.
In order to calculate forces exerted by moving fluids and to calculate other effects of flow, such as transport, we must be able to describe the dynamics of flow mathematically. To discuss the dynamics, we have to be able to describe the motion itself. The description of motion is called kinematics. We will be interested in the kinematics of continuous media, that is, in describing the motion of deformable stuff that fills a region. Specifically, we'll be interested in describing the displacement, velocity, and acceleration of material points in the two reference frames commonly used in fluid mechanics. We'll show how these two descriptions are related to one another. In addition to moving from place to place, an elementary piece of fluid is generally squeezed or stretched.
So in here, what's going on with this fluid? What would you call this?
Stretching?
Well,
Ish?
well, no, this parcel of fluid, this little rectangle of fluid is really, this is what we mean by deformation, right? It's being deformed. And the deform can be stretching, it can be turning. So that's what deformation is. And you say, oh, this is being deformed. And you have to think of a lot of things about how fluids are going to change over something.
We are going to focus our attention on the translation, not on the deformation.
There you go.
In this flow of water through a contraction, hydrogen bubbles have been used to identify pieces of fluid so that we can follow their motions.
Now, do you agree?
Effects of flow, such as fluid mechanics.
So in here, what's going on is you've got deformation, right? This is deforming the fluid. So they start as little squares as the fluid must go into this smaller tube. Okay, so we're not going to worry about the deformation of it. So instead of using squares, what are we going to have to use? What will be necessary?
Vectors?
Well, we'll use vectors, but you have to consider it as
In this
points.
flow of water through a contraction, hydrogen bubbles have been used to identify pieces of fluid so that we can follow their motions. These pieces are quite large, however, and we would like to examine the motion of very small, infinitesimal bits of fluid. Therefore, it will be more convenient.
One thing to keep in mind too is, do you see the shape of this square? It actually is doing something like this. It looks like that. Mm-hmm. What is this? What does this illustrate? It does the same thing up here. What is that deformation a result of?
Oh, viscosity.
Right? It's viscosity. That's what's happening. So you have incredible amounts. If you looked at a zoomed in area, you'd have incredible amounts of what? What does viscosity result in?
Stretching?
Well, it does a little bit, but what is it resulting in here?
Hearing?
What does this illustrate? Over here, it's shear, right? So viscosity creates shear. Shear results in what?
Yeah, from me.
Shear results in what?
Vorticity?
Vorticity, right? So if you think about what's going on in the surface boundary layer, you are talking about huge amounts of vorticity that's generated. And that's why when you see wind blowing, you'll see swirls all the time. Those swirls are a result of viscosity due to the frictional surface layer, causing extreme amounts of vertical wind shear that can get, with rising air, because it moves over surfaces, you get vertical motions that turn vertical vorticity, and you get these swirls that go everywhere. So whenever you watch leaves flowing, you'll see these swirling leaves. That's all because of viscosity due to the boundary layer. So I just wanted to point out some of the things that you should note about life in general. Oops.
Describe the motion itself. The description of motion is more convenient to have a computer simulate these motions and generate the visual displays for us. We will use open circles, as we are doing here, to identify material points.
Okay, now let's think about this for a second. What was the word that he just used for these open circles? He called them material points. If something in this point changes over time, then we would do this. Because it's a material point. It becomes a total derivative. Right? And it's a total derivative, meaning it's following a point. So that's where we get this idea of Lagrangian. Following the parcel. This time it's a point. They will use closed circles to be the local derivative, right? Which they call, what do they call that? They call it a...
Laboratory.
That's the word I'm looking for. Laboratory. Laboratory point. It's fixed in space. Okay? And so here we would use d something, d time. And then the question that you have to ask yourself is, well, how do these relate to each other? Now, in meteorology, which one do we measure? The laboratory point or the material point? What?
Oh no, the laboratory, because we can.
The laboratory point, because the laboratory point, what do we call measuring stuff at a laboratory point?
Well, the stations. Oh,
Yeah.
Bob, it's Bob.
It could be Bob, it could be ASOS, Bob.
It could be that weather thing I've got in the backyard.
So we say, this is what's happening at a point. Now, we send up a balloon, the balloon goes a little bit. It's not really moving with the air, but it moves down, but we have a location of those points. Okay, so that's basically what we're doing, is we're doing ASOS are measuring laboratory points. Because that makes sense. Because if we wanted to measure the temperature change of a material point, what would we have to do?
You'd have to be in a plane and take points like while you're traveling with the air.
Well, yeah, but you'd have to be traveling exactly where the air is.
Same speed, yeah.
So sometimes you'll hear people use this term. a neutral density balloon. Because if you have a balloon whose density is the same as the air that it's in, it will move with the wind. Then you're measuring a material point. But that doesn't, you don't do that very often. There are times where you'll see research where they do something along these lines. But this is much harder to do. So we are going to measure everything in laboratory points. And what really matters is the parcel has to have forces. It's the parcel's change that matters. Because it's the parcel that, if there is a pressure on it or a force on it, do you agree that's going to cause an acceleration? And that acceleration is going to move the parcel in different directions. So I need to know how to get this, but this is what I measure. Does that make sense? I measure the laboratory points, but I need the information from the material point. And that's what this movie is all about.
To describing the position of a material point as a function of time, using a vector drawn from some arbitrary initial location to indicate the displacement.
Do you understand what they've done here? This is an open vector. This open vector is actually what the material points vector is. The only difference is, where are we placing that vector? We're placing it at a fixed point. So this vector, the open vector, is the force or the velocity or whatever vector is associated. Open vector is associated with material point, but placed at a fixed point. Okay. Does that make sense, guys? Do you understand what I'm saying here? Yes or no?
Because that's the instantaneous measurement, right?
Right, but it's the measurement of the actual point,
Yes.
not the location. I'm just putting that vector at the location. So watch what's going to happen at this point.
We will use open vectors, as here, to indicate velocity and displacement relating to material points, open points. In a given motion, we can compute the velocity and acceleration of such a point at each instant. Here we indicate the velocity by a vector attached to the point. In a continuous fluid, of course, we have an infinity of mass points, and we have to find some way of tagging them for identification. A convenient way, though not the only one, is to pick some arbitrary reference time, which we will call the initial time, and identify the material point by its location at that time. Mathematically, we would say that the velocity is a function of initial position and time.
So that's the open vector following that point, displayed at a fixed point.
To accord with this description, we have shown the vector attached to the initial position. We could show the vector attached to the moving point, or use both. If we were displaying the motion of a group of points like this, whose vectors do not interfere with one another. To display the whole motion, and in more complicated situations, we avoid interference by showing the vector only at the initial location. To describe the whole motion, we would have to give the velocity of all the pieces of matter in the flow as a function of time and initial position, like this.
Okay, does that make sense? Do you understand what they're doing? Now, I've seen this so many times, it makes more sense the more that you watch it. But I'm just showing you all the different points, because how many points exist in here?
Infinite.
An infinite number of points. And I'm just choosing some of them and representing a vector of what that point does later. So he says the velocity is a function of its initial location and time. Make sense? Because where it is, these arrows are not all the same because the initial velocity was different when I started this thing.
This description in terms of material points is called a Lagrangian description of the flow. Such coordinates are called Lagrangian or sometimes material coordinates. From the Lagrangian velocity field, we can easily calculate the Lagrangian displacement and acceleration field. We can imagine attaching an instrument, like a pressure gauge, to a moving point to make what we might call a Lagrangian measurement. This sort of thing is attempted in the atmosphere with balloons of neutral buoyancy. If the balloon does indeed move faithfully with the air, it gives the Lagrangian displacement.
Sorry, neutral
Lagrangian
buoyancy.
measurements are actually very difficult, particularly in the laboratory. We usually prefer to make measurements at points fixed in laboratory coordinates. Classically, the idea of a field, such as an electric, magnetic, or temperature field, is defined by how the response of a test body or probe, like this anemometer, varies with time at each point in some coordinate system. Here we are probing in laboratory coordinates. We will always indicate such probing points, points in a coordinate system fixed in our laboratory, and the velocities measured there by solid points and solid arrows.
Okay, you guys follow that?
But I didn't quite hear all of it because of the weird distortion from the watching it through a screen share.
Oh, okay. How about the rest of you? Were you able to hear most of that?
Yes.
Okay. So all he's saying is that we now have laboratory points, right? So in meteorologists, what do we say? The world is our laboratory because we're dealing with the entire atmosphere. And we put sensors every place in that laboratory. And that's the words that they're using to describe the fact that we're taking measurements at fixed points.
All right.
Now let's get into the math of it all.
Here is a grid of points fixed in space. We show the velocity at each point.
By the way, a gridded laboratory fixed in space. Anybody want to tell me what we are describing here? A gridded laboratory?
Model.
That's a numerical model, isn't it? We collect data. We do something called an objective analysis. We find ways of taking data points and assigning it to a grid. That is an initialization of a grid. And there's a lot of research, there's a lot of stuff you would do in modeling that talks about how that happens. But you're basically saying, I'm going to take these temperatures and I'm going to assign it to a grid. And there's methods to do that. And so in actual models, what they do is they assign it to a grid, they run it for a little bit, and then they adjust it. So not only do they do that initially, but they massage it and they adjust it so that it gets more and more accurate. Because obviously, if I'm taking a temperature at DuPage and at Midway and at O'Hare, what the temperature here can be different than all of them. So I have to find a way to assign it. Would you agree, though, that all modeling has an initial error because it's not exactly precise, right? We don't have extreme precision in doing this. Therefore, we have an initial error. Therefore, chaos theory says eventually that error will take over and the atmosphere becomes non-predictable. If we ran the NAM with a perfect grid, with perfect precision, we'd have a much better model. But we don't do that. That would be a really interesting way if we could put a grid equally spaced everywhere of exact precision. I wonder if our models would get better. Anyway, going on.
A description like this, which gives the spatial velocity distribution seen by a probe in laboratory coordinates, is called an Eulerian description of the flow.
Notice, guys, that the white arrows are not moving over time because the fluid is moving, and this arrow is exactly what the fluid is at that point. So the question I'd ask you, before we show this, what would cause this arrow to change at that point? Do you guys understand what I'm saying? What I'm talking about?
Yeah, just writing down something.
Here, we're watching this simulation. All these particles are moving through this tube, right? All of this stuff is moving through this funneling tube. Okay, and the parcels or the little particles are going to accelerate as they go into a narrower tube, right? You take a hose, you squeeze the hose, it's going to go faster. Okay, so what we're saying is that there's an acceleration of each individual parcel. But over the course of time, at this point, does that velocity change? So what you would be saying is, based on this alone, this velocity at that point, as I run this thing through, those arrows never change. So I would say this. Right? It's not accelerating. So what would cause this arrow to change?
Change in the Lagrangian flow?
What do you mean by that?
I guess just a change in the overall flow in general.
But it's the same thing, right? Everything's the same. What is this a function of? The initial location and velocity, right? We are starting the parcels here with an initial velocity. Well, what if that velocity, if something changes in the initial condition, won't that change this one?
Yeah.
So that means from here to here, there would be a change if the velocity changed over a distance. So if I had some change in velocity over a distance, what do we call this?
Acceleration.
Well, yes, but what do you call anything, a change in anything over a distance?
Gradient.
Okay, if there's a gradient, then these things will change. Keep that in mind. But do you see now that I have a spatial term instead of just a temporal term? Okay, so I want to make sure you know these words. This is going to be X, Y, Z. This is going to be T. Those are your four independent variables. Time, and by the way, most people nowadays go temporal because that's, I don't know why. When I grew up, it was always temporal. Jim, do you know that?
I've always known it as temporal.
You've always called it temporal? I always knew it as temporal, and now everybody calls it temporal. But, I mean, we're talking 35 years ago, it was temporal and spatial. So if you're going to call it temporal, I'm going to call it spatial.
No, it's Spätzle for German.
It's going to be spatial. It's very spatial. Okay, continuing on.
Although the physical field is the same, the Eulerian and Lagrangian representations are not the same, because the velocity at a point in laboratory coordinates does not always refer to the same piece of matter. Different material points are continually streaming through the same laboratory point. The velocity that a fixed probe would see is the velocity of the material point that is passing through the laboratory point at that instant.
Does that make sense?
Mm-hmm.
I think that should.
It's an advantage of the laboratory coordinates that there's often a frame of reference in which the Eulerian field is steady. Just as we simulated the flow in the contraction, we can simulate the flow under a free surface gravity wave like this. To make things clearer, we have rather exaggerated the wave amplitude. Let's take a closer look.
Okay. Let's stop for a second. I have a gravity wave. It's just a wave. Now, do you remember what a wave is? What does a wave do? Let's put it that way. What does a wave do?
Has frequency and amplitude.
What does it do?
It oscillates.
Yes. But a wave transfers energy.
Oh,
What does it not do?
what does it not do?
It doesn't transfer mass. It transfers from here to there some energy, but it doesn't transfer mass. What do you call, like if you think water, what do you call the mass transport of water? What's that called? What'd you say, Allison?
Wave?
No, a wave does this. It makes those little circles, right? But what do you call a mass transport? In other words, you're transporting mass, and that mass is water. There's a name for that. What do we call moving water?
Flow.
There's a more common name.
Torrent?
What?
Like a torrent?
No, simpler. Think oceans.
Current?
Wave?
Currents. Currents are transferring mass. You have a flow, and so Michael, that's what a current is, right? It's a flow of water. But a wave just transfers energy. So in this picture, what is this down here?
Down where?
Is that turbulent eddies?
See, I knew that was causing problems. That's the ocean floor.
Oh.
That's just the artistic. It's an artistic representation of the floor of the ocean. And I know that you know that because it's like, what the hell is this thing?
Why
And it
can't
looks like eddies. And I knew that you would say that. That's pretty funny.
Why can't they just draw a straight line? Why do they gotta draw like little plants?
These are moving material points and their path lines.
So what do you know about the path of these circles?
Equal distance.
That was stupid. Have you ever been to the ocean, floating, like just floating in the water?
No.
You go forward and backwards, and you go up and down. Now, given that something is moving in a circle, do you agree that a circular motion is this way and this way? And it's up and down at the same time. So if I go up and over, I do this, right? That's what I'm getting with my vectors. I'll get a vector that does this. So what causes a vector, or what causes this parcel to move that way? Why would this parcel move that way? Sorry, that's why I played this. The parcel is not moving that way right now, but a parcel. So let's say anything. Let's say any dot. Whoops.
Here are the velocities of the moving point.
Actually, let's go back just a little bit, okay? What would cause a parcel is moving it back and forth. So if a parcel starts moving, is moving this way, why does the parcel go in a circle and start coming back that way, given this configuration?
Because the wave is at maximum amplitude.
And what am I measuring? What do you call the weight of the water above you?
Water pressure.
And what do you call the weight of the water here? Do you agree it's going to be greater pressure there than here? So
Right.
which way is the force pointing?
That direction.
So the parcel's moving that way, but there's a force slowing it down, which now at this point, what is the velocity of this parcel? The velocity of this parcel is neither left nor right, it's tangent to the circle. What is the velocity here?
Tangent to the circle.
And do you agree that I have a component this way, and over here, it's a component that way?
Yes.
So there's an oscillation horizontally. And the same would be true with the vertical gradient. So we make these little circles. And that's kind of what's going on. Now, if you were doing that in a shallow water wave, I want to make sure this is right. No, in a deep water wave. A deep water wave will have bigger circles up top, smaller circles down below. And if you go into the tsunami met-ed, and I know we've done that in my 1119, they show you these particle motions. So when a tsunami comes on shore, the motion gets stretched. So this circle, instead of being a circle, gets stretched, and that's why water flows on land and then it comes off land. It's making these circles that you're now squishing, and now they accelerate horizontally, really, really long. Anyway, I just wanted to point that out to you because I think it's interesting, and I want this class to be interesting.
Here are the velocities of the moving points. The Lagrangian velocities attached to the points. And here also attached to their initial locations. In any flow, the Lagrangian field can only be steady if each material point always experiences the same velocity. This degenerate case only happens in a steady parallel flow. Here now is the Eulerian description. In this wave motion, neither the Eulerian nor the Lagrangian description is steady. In fact, they have an identical appearance.
Isn't that cool?
In this flow, if we move our frame with the wave speed, the Eulerian pattern will become stationary. Let's do this and
This is
indicate
cool.
the translation velocity by an arrow at the bottom. Now let's resolve the velocities into components.
Okay, did you guys follow what he's just done here? They've taken this wave that's oscillating in a steady state. Those are the words he was using, a steady state flow. But now, since the wave is this way, and there's a frequency and a propagation speed of the wave, what we're going to do is we're going to translate opposite that so that the wave becomes a standing wave. That's what this arrow on the bottom. So the arrow on the bottom, this guy down here, became larger and larger as you moved with it. So now you see the ridge of the wave is always fixed in our viewing screen. And then they're going to show you what the parcels look like.
The horizontal component is the velocity with which our frame is translating. The other component is the material point velocity in the original frame of reference. Let's see that catch up again.
So these are all the Lagrangian, these are all the Eulerian points, and you're making circles. But now, as you move this circle in a fluid that's translating, now you get a wave. Do you remember, where am I? Do you remember in 11:15 when we drew circular motion with translation? And instead of being circles, if we translate faster, it never goes back on itself, and so we get a wave pattern. And that's what those parcels are actually doing. They're traveling in waves. So when I translate, this is a big translation, much larger than the little vector showing you the circle, you don't see a circle, it doesn't back up on itself, and you get a wave pattern. If I were to make this arrow smaller than this arrow, then I would make what? Well, what would the shape of this parcel be? You remember what we did in 11:15? It makes little spirals. And doesn't a tornado rotate faster than it translates usually?
Mm-hmm.
Not always. When we had our QLCS this summer, we probably did not have rotation that exceeded the translation, which made it much more difficult to find damage because the damage would not have gone east in one direction and west in the other direction. It would have all been going to the east, but we would have seen some of the damage going to the north and some of the damage going to the south. We would have seen the north-south oscillation, but not east and backing up. And we actually did see that.
The path lines, which are also streamlines in this frame of reference since the flow is steady,
The flow is steady, so it's a streamline, as opposed to a trajectory. So in this case, where we're saying trajectory streamline is the same because it's following the same path.
resemble the form of a free surface. As a material point passes through each laboratory point, its velocity is instantaneously the same as that of the laboratory point. It is partly this possibility of eliminating one of the variables in the analysis, time, that makes the Eulerian representation more attractive. Most laws of nature are more simply stated in terms of properties associated with material elements, Lagrangian quantities. But it's nearly always much easier mathematically when describing a continuum to deal with these laws in laboratory coordinates. Thus, to write our conservation equations, we have to talk about transforming from one set of coordinates to the other. Let's talk first about the relation between.
Hold on. Um, um,
Frame is transparent representation of a river in which a radioactive tracer has been. The
So-
path line,
so,
which are
did you notice he was way off on his mouth and the audio gets way off? So somebody went in there and actually did an audio fix of this stuff. So I should put this one out. This is better.
also streamlines in this frame of reference, since the flow is steady, resemble a form of the free surface. When describing a continuum, to deal with these laws in laboratory coordinates. Thus, to write our conservation equations, we have to talk about transforming from one set of coordinates to the other. Let's talk first about the relation between time derivatives in a scalar field. Let us imagine a river.
So what they're going to do now is they're going to show you the first example, which is a time derivative of a scalar field. So they're going to talk about a concentration of a radioactive tracer. So they're going to use R. We could easily, and maybe I should, is call it T. So we could use it as temperature. So which would you rather use temperature or you want to use R the way they have it?
Temperature.
Let's try temperature.
Which a radioactive tracer has been distributed. Since we're interested in local changes, let us look at an infinitesimal part of this river.
So I'm zooming in into just a part of the
Now
river.
let us imagine that the tracer is suddenly and uniformly distributed in the river.
And so well, you know what? I think I will use R just because it's kind of cool. So what did they just show in the last few seconds here?
Oh, the tracer being uniformly discharged throughout the water.
Right? It's uniformly distributed, but what happens to the radioactivity?
Now let us imagine
In this
that the tracer
picture.
is suddenly and uniformly distributed in the river.
It looks like it's shaking, but I can't tell if that's like.
No, you see how it's fading?
Yeah.
So what's happening is the radioactivity of this thing is changing over time. Where is it changing? Everywhere. So if I had a parcel here, the radiation in that parcel, shown by the big dot, as the parcel goes here, the parcel will get fainter until it eventually fades out to nothing.
So it's a negative quantity.
Well, but do you agree that I could say that of the parcel?
Mm-hmm.
the radiation, the radioactivity level in that parcel fades over time. So it becomes, the change is less than zero, so it's negative. But you could also say that at a single point in time, it starts fading also. So what would that single point in time be?
Del R over del T.
No, not del.
Partial.
Partial. Partial R over partial T. And that would be zero. So in this case, partial R and the total derivative R are the same. But that's because it's uniformly nothing. I mean, it's all the same. Now, I want you to think about this for a second. When we used the derivative in class, let's say that we did this, we said it's going to be equal to dt dt minus that. This is the advection term. Remember we did this in class? So if I, and again, in 3 dimensions would be u dt dx plus v dt dy plus w dt dz. That's what it is. This is a dot product, so it's a scalar quantity. But what is the unit of u? Or what is u actually? U is dx dt times dt dx. From a unit standpoint, the dx's go away and I'm looking at the change over time, which is good. I can't, do you see why I can't just cross this out? I can't just cross that out. That's illegal. Because this itself is a quantity. It's how does x change in t? How does my location change? It is a velocity. And this is a unit amongst itself. It's the gradient of the temperature. But from a unit standpoint, the units work out. Okay. But in this case, is there a gradient in the radiation?
No, they're all the same.
Right? I uniformly distributed the radiation over the course of time.
These dots that are gradually disappearing symbolize the tracer, which is gradually decaying everywhere.
It's decaying
These filled-in
everywhere.
circles represent 2 laboratory points, which are infinitesimally close together on the same streamline, but which look far apart in our expanded view of the river.
Right? It's, how close are these together?
Infinitely close.
Infinitely close. So what's the distance?
0.
No.
The dx, I guess.
Right. They're dx distance. That's dx is infinitely small. Does that make sense to you? They look far apart, he said, but they're not. They're infinitely close together because we're using derivatives.
Since in this case we distributed the tracer uniformly, the radioactivity at the 2 laboratory points is the same, but is changing with time. We can add radiation counters at the laboratory points.
So that's just how much radiation. That's how.
The solid bars on these Eulerian radiation counters indicate the level of radioactivity at these 2 laboratory points.
There's a parcel moving with it. That's the material.
We can monitor the level experienced by a material point traveling from one laboratory point to the other by watching the open bar on the Lagrangian counter carried by it. The dashed bar represents the value recorded by the Lagrangian counter as the material point passed through the left-hand laboratory point. Comparing the before and after values of the Lagrangian counter, it is evident that the traveling points see only the same change that each of the laboratory points sees. This can be written as the time difference multiplied by the rate of change with time.
Right? So delta T is the time change times the way that the radiation changes over time. This is happening at this point. Right? This is a partial derivative, therefore it's the Eulerian description here. So all I'm saying is that it changes by, let's say, what what do they call the amount of radiation? What's the unit? Curies?
Curies.
Curies, yeah.
So it says it's going to change by 2 curies per second. Times 3 seconds, how many curies did it go down? 6. Right, that makes sense. That's the total change. So this equals that. The rate of change times the time is equal to the total change. Does that make sense? I think this, this should be. That makes sense, I think. Oops.
Suppose now, however, that the tracer is not uniformly distributed in the river, but that the intensity is greater upstream.
Would you agree there's a gradient?
Yep.
Now the intensity at the downstream point is initially lower, and of course both are decreasing with time as before.
So the partial of R with respect to time is equal everywhere.
Just as before, the only change experienced by the material point is due to decay. The change seen at a laboratory point is not, however, since new material of originally higher intensity is being swept past. To express the change experienced by...
Do you understand what he said there? The parcel experiences the same decay that it did before. It's decaying the delta T times the rate of decay. That's of the parcel. But the point, which would experience the same thing, is being fed by higher radiation coming into it. Okay, so think about temperature. So what do we call that? You're muted. What do we call that?
Advection?
That's advection. We are advecting material in.
Point in Eulerian variables, we need two terms. The change of intensity with time at a fixed point and the intensity difference between laboratory points at a fixed time. The total change when the material point has reached the right-hand laboratory point is given by the difference in level between the dash counter on the left and the Lagrangian counter. The change with time experienced by either laboratory point is given by the difference in level between the dash counter and the Eulerian counter on the left.
Okay, that's a lot of words. You'll see what it means in a second.
Be written as before as the time difference multiplied by the rate of change with time.
Right? That's still at the point. This is still the rate of change of time times the time. It's not the same as the big one because the rate of change is going to be different. Let's continue.
The change due to the intensity difference between the laboratory points at any time is indicated by the difference in level between the two Eulerian counters and can be written as the distance traveled multiplied by the spatial gradient in the direction traveled.
Okay, so right, so just like this is a time derivative times the total time, this is a spatial derivative. We could use the word zonal derivative times the distance traveled in the zonal direction, in the east-west direction.
The distance traveled can be written as the time difference multiplied by the magnitude of the velocity.
Okay? So now they're replacing this delta x with delta t times u, the velocity.
The total change is the sum of the two changes described. The material or substantial derivative is the name given to the expression multiplying the time difference.
So that's the material. And here they throw in a third word, the substantial. We've been calling it the total, which I like. So the total change is a result of this temporal change and the spatial gradient times the velocity, which is an advection.
This is simply the rate of change with respect to time seen by the material point as it passes the laboratory point, expressed in laboratory coordinates. Since this derivative operator occurs in every Eulerian conservation equation, we give it a symbol in fluid mechanics, using capital D's to emphasize that the material derivative is the rate of change seen by a material point.
Okay, so what they're doing here is this. Let me get my pen. They are saying that this equation is equal to the total R. Then they divide both sides. Right? They get rid of this over here and bring it over here. So they're saying, how much does the radiation change in a given amount of time of the parcel of the guy that moves across the idea? So instead of doing this, they now use capital D. And that's what's known as the total derivative. Right? But we've been using dt. And I'm not sure why it went from this to this other. I don't know where that came from. Maybe that happened since this movie was made. I don't know. All I'm saying is that this is dt. So whenever you see, I'm sorry, dt. Whenever you see that, this, you can think that.
In my class, they use the big D when they're talking about the Lagrangian, just so that they can differentiate between.
Right, but it's sloppy. So anytime you see this D or that D, this, I mean, if it were my world, I would want to use the capital T. I don't think the textbook does. But this makes sense that that's total derivative set up by partial derivative. This becomes, I think what happens is we're just sloppy. I think mathematicians are sloppy and we interchange things too often, and that's a problem. So you have to realize what is going on. So when I look at this thing here, I'm saying the total change that a parcel will experience is a result of what is happening over time, and that's this counter is showing you this decay, plus the spatial change, which is over here. And since it's the velocity times a gradient, velocity times a gradient is advection. And you better, I'm telling you, you got to know that. It needs to be your second nature. Velocity times a gradient is advection. Actually, velocity times anything is advection. But in this case, we want, that's advection of, actually, if I really want to do that, that's advection of a scalar quantity. Can you get advection of a vector quantity? And the answer should be yes. Because what is this over here, folks? What is this term? Do you agree that's a scalar term?
Mhm.
So I need a scalar term here. If instead of this, we use a velocity vector, then this has to be a vector.
As it passes a laboratory point, but expressed in laboratory coordinates. In vector notation, the velocity times the gradient in its direction can be written as the scalar product of velocity and the gradient.
Okay, hold on. So I'm multiplying by the vector of velocity. But since I'm doing dot, so it's basically this. I could take, they're using U, I can make three-dimensional times del times the scalar quantity. And I would draw it this way. They put parentheses around it, which doesn't really matter. They don't put a vector on this del. And I'm not sure why, unless they just assume the del is a vector.
Wide.
What?
I think it's implied.
I think it's implied, yeah. They may just say del is a vector.
We're also interested in the material derivative of a vector field, such as the velocity. We're especially interested in that because the material derivative of the velocity gives an expression for the acceleration in a form which we need for the momentum equation. The expression that we just obtained for the material derivative of a scalar field would work just as well for each component of a vector field. But we can also show the material derivative of the vector field directly. Here are two laboratory points infinitesimally close to one another.
So again,
a
dx.
magnified view of an arbitrary steady flow. They lie on the same path line, and the material point is traveling from one to the other.
So you're basically
The
saying,
velocity of the material point is indicated by an open arrow.
you're basically saying that there is a path, he said path line, looks like this, right? And what would you call that path line? What's a better name for the path line?
Trajectory?
Wave.
That's a trajectory.
That's right.
That's for trajectory. If it's not changing over time, so that all parcels go on that same thing, then it could also be a streamline if it's steady state. In other words, if that streamline doesn't change over the course of time. Then the streamlines and trajectories are the same if they're not changing.
Attached to it. Clearly, although the flow is steady in the laboratory frame, the moving material point experiences change as it travels
So it's
to regions
accelerating.
where the steady velocity is different. The total change will be the difference between the velocities at the two laboratory points, indicated by the solid Eulerian vectors.
So in here, these solid vectors,
The amount of the change will be easier to see if we
these solid vectors are the steady state laboratory point velocity. So I have a velocity at the left point, a velocity at the right point, and they stay the same. They're different. So the parcel has to go from this velocity to that velocity. Now, it's a change in a vector. So in this example, we're going to have a vector, oops. We're going to have a vector here, and then this vector here will be put down here. So the vector change is this. Connect the head of one to the head of the other. That is and you will see this, that is a change in the vector. That's how the velocity is changing. And it is the change in the velocity over time that defines an acceleration. Okay? So keep in mind that's how you do vector differencing.
we attach the Lagrangian vector to the left-hand laboratory point, taking as our initial or tagging time the time when the material point passes that laboratory point.
So we start it here.
The difference between the Eulerian vector and the Lagrangian vector, the left-hand point, gives at each instant the change that the material point has experienced. The total change when it arrives at the right-hand point, a vector distance delta r away after a time delta t, can be written as the vector distance traveled times the gradient of the velocity.
Okay, hold
The
on.
distance traveled is just the time difference.
So, what does this say? Well, let's go back just a little bit.
When it arrives at the right-hand point, a vector distance delta r away after a time delta t can be written as the vector distance
Delta r away. That's a distance.
traveled times the gradient of the velocity.
Do you agree that there's and here they're using u, but it's really velocity vector. So the velocity vector changes. There's a gradient in the velocity. This velocity is different than that velocity over a distance.
The distance traveled is just the time difference times the velocity.
Right? So I know a velocity times the time should be the distance. So they're using r rather than x, which makes sense because x in our mindset is actually what? It's a distance in what direction?
West-east direction.
Correct, right? It's a zonal. So in mine, it's a zonal direction. If I used y, it would be a meridianal one. So what they're saying is instead of using x, I'm going to use r. So we would sometimes think delta x. But since they're not doing it in x and y only, they're using r instead of x. But now, oh, shoot.
In order to
Like,
the
yeah,
change
that's about right. It was around like 2115 or something.
Say that again.
Wasn't it like, I think it was like 2115, I believe. Something around there.
That's a little bit later, I think.
and laboratory
Oh, no.
at this instant time, as it does here.
Close enough.
Eulerian vectors also change with time.
Well, we'll just do it one more time. Did I go too, am I too far ahead? Did I do
No.
this? No, I'm okay.
Yeah, it's fine.
No, it should have been here.
Yep.
Now, if the velocity of the entire flow changes with time, as it does here, the Eulerian vectors also change with time.
So the first one, just like the radiation was a steady distribution, now we have a changing distribution. So we are accelerating at the laboratory points. See how this laboratory point is changing? So the moment the material point goes through the laboratory point, that's the same. But now the laboratory point is changing. So you're imposing accelerations of, you're changing the streamline. So now we have to go to a trajectory.
It will be easier to see if, in addition to placing the Lagrangian vector at the left-hand point, we include as a dashed vector the initial value of the left-hand Eulerian vector.
So right there, what we're saying is that this, let me do it this time. This arrow is what? What's this arrow?
The original trajectory.
The original,
Initial.
the initial velocity at the laboratory point.
Mhm.
This blue vector is the velocity later. So the difference from there to there is a result of what? That's a change in the velocity at a point over time. Right? That's what that one would be. It's the local change. This vector is the total change. That's the total change. But this vector, oh, I'm running out of colors. The pink plus the orange is going to be the green. So let's try that.
Now, when the material point has arrived at the right-hand laboratory point, the total change it has experienced is given by the difference between the dashed vector and the Lagrangian vector. But this can be broken into two parts. The difference between the velocities at the left and right-hand laboratory points at this instant is given by the difference between the Eulerian and Lagrangian vectors on the left. The change each laboratory point has undergone during this time is given by the difference between the dashed and Eulerian vector on the left. The spatial velocity difference can be written as before as the time difference times the velocity times the gradient of the velocity. The temporal velocity difference
See,
can be
temporal.
written as the time difference times the rate of change with time at a laboratory point. To find the total change, we must vectorially add the two effects. The material or substantial derivative is just the expression multiplying the time difference. This is the rate of change seen by the material point as it passes a laboratory point, written in laboratory coordinates.
Okay, so do you see that our way of drawing
In
things,
this way, the acceleration, more simply written in a Lagrangian description,
what we would draw, or the way that we would define this, is we would say that the change of a velocity vector over time, the total derivative, is equal to the local rate of change of the velocity vector over time plus the velocity dotted with the gradient of the velocity. And the way that we might want to think about this is that we would do this. Here's kind of the little trick. So I just had to think this. If I dot two vectors, what do I get?
another vector.
No, if I dot
Magnitude.
Scalar.
I get a scalar. If I have a scalar times a vector, what do I get?
A gradient.
Gradient. Okay, so they will do this.
Does
And
it
that's
make
all-
a difference?
That's all they're doing. But it's the same thing. And if you worked out what the velocities are in terms of its I, J, and K component, et cetera, you would see that these all come out to be the same. So this is the way that we do this, but we don't do it this way because we are concerned about measuring this. So we say dV is equal to minus that. That's the way we think. So we tend to do things with the minus sign because this is the information we are given at a point. And this is what matters because the parcel is doing the acceleration. So we use kind of both ways. But your book will talk a little bit about that. Okay? Can I erase this?
Just one sec, sorry.
Okay?
Good.
Has been expressed in Eulerian notation. To summarize what we have seen, we can tag the material points in a flow by using their locations at some reference time, and then give their displacement, velocity, and acceleration as functions of time and initial position. This is called a Lagrangian description. Alternatively, we can define a coordinate system arbitrarily and probe to find the displacement, velocity, and acceleration at points fixed in that system. This is called an Eulerian description. This has the advantage that it is sometimes possible to find a system in which the flow is steady. It is also mathematically enormously more convenient. We nearly always write the conservation equations for a continuum in this Eulerian system. It has the disadvantage that we're not always referring to the same material point. We can, however, transform from one system to the other by using the fact that displacement and velocity in a laboratory point is the displacement and velocity of the material point that happens to be there. To express in Eulerian field variables the change experienced by a material point, we must take account not only of the change with time of properties at a fixed point, but also of the change of properties with position at a fixed time.
Powerful mathematics, isn't it? And then I like that he does a description of this, and then it just ends. Now, do you agree that this would be so awesome if it were updated into current technologies where we could use colors and all sorts of stuff? But it's good. I mean, this is a great, great video. And this is why there's so many people who actually to do this. I've gone through each video and manually synced all the videos. I'm going to do another thumb. I just added one.
Great cure to sleeping problems.
Yeah.
Yeah, if you want to do this, you would definitely do this. So
Oof.
I don't know anything like this. that makes it this descriptive. But I really think it's really impressive. Now, the last thing I want to do is I'm going to look at chapter 6 in your book. We still got some time, so not 6, 7. So turn to page 273.
Ooh.
Okay, and we have this equation about divergence, which is del dot V. So it says del dot V
273, you said?
Yep. Okay, do you agree that del dot V must be a scalar? So divergence is a scalar quantity. What they are doing, and they say div H of V. So that's what the book says. What they're really saying is I'm just going to look at the horizontal. I'm looking at 2 dimensions. We could do this in 3 dimensions, but I'm looking at 2 dimensions. So in that case, we have a square, right? There is a square. And if there's divergence, what would happen to this square if there's divergence within it? What happens to the square if it's divergent? It expands. So what we're saying is that there will be a change in area over time, which is equal to, and here they're going to use delta x, small delta, delta y. So they're saying that it's the change in delta x times delta y all over time.
How do you draw the delta symbol again?
It's like that.
Okay, it's a music note. Gotcha.
Yeah, it's kind of a music note. So however you want to draw that. And then they're going to say that this is going to be delta y times the derivative of delta x over delta dt plus delta x equals d delta y over dt. Now, boys and girls, what did I just do to go from here to here? What is this?
Product rule.
Right? That's all I did. But it's weird because you're saying the change in delta x, which is actually, what is this equation then? How would you say this? You'd go,
That's a good.
that's a question. What is the question asking? What is that question in English?
How is the box stretching over time?
Yeah, but how does what change? What is delta x?
How does the velocity of x change over time? No.
No.
Horizontal distance.
How is the location?
Well, it's not the distance, it's a
Location?
Isn't this a change? How does the length of the side change over
Literally. Okay.
right? So this is the length, just like this is a length. So why would this length be changing? If it's a box of partial, if it's a square moving through space, that's weird. So in other words, the reason that there's going to be a change is because this side of the box has to be going at a different speed than that side of the box. So you're saying that this thing in red is actually going to be, oh, I'm drawing with vectors. Times the change in u, whoops, the total change in the velocity. But the total change in the velocity is going to be the rate that the velocity changes in the x direction. Because do you agree that what would we call this change in velocity? That's a what?
Acceleration.
Well, it is accelerating, but what else could we call it? I mean, we don't call it this way, but it is. It's a velocity gradient, right? It's a change in something over a distance. It is a velocity gradient. It's the u velocity gradient, and it's changing at an infinite number, or it's an infinite number, it's an infinitely small distance, the velocity changing, times the what? The total distance that it's traveling. But that's multiplied by delta y. So in other words, this becomes that. This, the total change in u, becomes this.
Both terms.
Right? But what do I have? Delta y times delta x is what?
The area.
Yeah.
But isn't that the area? Oops. Let me clean that up. That's the area times the velocity gradient. But that's only the first side of the equation, right? In other words, this area here, this thing here, is only this side of it. Right, so that's this. So what I need to do is, well, what would this be? That has to go in here someplace, right? So what would that be? It'd be the same thing, plus the area times, but instead of du dx, or the change, yeah, du dx, it'd be what? Sorry.
Du dy or dy.
dv
dv.
dy. Or it would be dA dt equals the area times du dx plus dv dy, or 1 over that dA dt equals du dx plus dv dy. Which is what equation 7.2 is in your book. Does that make sense? Do you follow what they've done?
Yes.
It's weird because you're using a derivative of a delta. So that's why I said the thing that you need to understand is the change in the length. And why is the length changing? Because it's divergent. Okay, so let's go into 3 dimensions, what would that equation look like in 3 dimensions?
Instead of the area, you'd use the volume.
Right? But if I have a volume, and here's the weird thing here. If I have a volume, watch my hands. If I if I stretch it out this way, what will happen to this way?
Should compress.
So imagine a parcel traveling through space and it's being deformed. Because it's a Vegas box, that parcel stays the same. So what we say is this goes to 0. Whoops. Because the volume doesn't change. If I have just a box that I'm stretching. In other words, du dx plus dv dy plus dw dz, which is really the velocity in 3 dimensions, not 2 dimensions, is equal to 0. That is called or the continuity equation. And we are going to do something so juicy on Tuesday. It's one of my favorite sections. Now, could I make the box expand in all 3 directions?
I suppose so.
How do I do that? How do I make a gas expand?
By taking.
Yeah, right? This is simple. Heat it. If I heat it, do you agree it's going to expand?
Yep.
Mm.
So I have to be very careful about what I mean by equals 0 for mass continuity, because if I change the temperature of it, well, then I can expand the gas differently. Then the volume does change. So just be aware of this. This is when I'm talking about 3 dimensions in the atmosphere. So if I take this, I also want to do something like this. So in other words, if I take the box and I expand it, then the air is going to compress. Push down, it expands. Which, that should make sense to you, right? If I took a box of air and I threw it to the ground, do you agree that that parcel would deform and spread out?
Mm-hmm.
But it's the same amount of mass within that area. So we'll reference this. So we did pretty good through this first section. So before we go to all of that, we'll come back to this later. I think what I'd like to do is I'm going to talk a little bit about this on Tuesday. But what I'd like you to do is finish reading the chapter. Well, no, read up to page 297. So you're going to study and take notes on up to 297. But I want you to go and look at page 293, 7.3.4. Because we're going to talk about this in a little bit of detail. So really study 7.3.4. Okay, so what you have over the week. Oops. What you have over the weekend is read the book 1 through, study 7.3.4, and then keep working on your project. Because I want to make sure you're doing a couple of problems a week. Okay, guys? Any questions?
Good.
Good stuff.
Well, I have to watch that video a few more times.
You
That
got
was
it.
really information dense, but
It's information dense. Yeah, you need to become fluent in it. So I would watch it again. That's a good one. I'm probably going to rename that video to Eulerian and Lagrangian. All right, guys. We'll talk to you later.
Yeah.
Bye-bye. Have a good weekend.